Okay, so what I want to absolutely finally do is discuss higher dimensional Lebesgue measure and integration. And the reason I want to do that is there's obviously no homework on this, and the final there's nothing on the final problem set based on this because the semester is over. But if you actually want to apply, Lebesgue measure and integration to different areas of applied and pure math, particularly probability theory, um, then you really need higher dimensional Lebesgue measure integration. And after this, or at the end of this video, I'll actually discuss and give you a nice source, particularly if you're interested in learning more about measure theoretic probability. There's a really nice, quick introduction to that area. And that introduction actually is a book on what's called stochastic differential equations, which is basically how to do like modeling and rates of changes with random processes, which is obviously extremely important. Most things in real life are random processes, like the stock market or lots of biological things that change in time. But anyway, okay, so, and then also I should mention this is very important for the PhD preliminary, and I know at least one or two of you are going to take eventually the PhD preliminary in real analysis. Particularly relevant to that is Fubini's theorem, which I'll discuss a little bit. But so the definition of Lebesgue outer measure on RD is not terribly subtle. It's basically the same definition as Lebesgue outer measure on the real line. The only difference is you replace intervals with rectangles. Okay. The definition of the volume of a rectangle. Well, I should say the definition of a rectangle. You did this in Calc 3 in 3 dimensions, and if you took, I forget the number, but if you took advanced calculus of several variables, I'm tempted to say 412, but anyway, if you took that, you probably did this. But anyway, what's a rectangle here? Just like in Calc 3, when d equals 2 or 3, well, there it's a box and a rectangle. But anyway, it's just a product of intervals. Some of them could be open, some of them could be closed. You could have a mix of open and closed. It's just a product, Cartesian product of intervals. Okay, you have D of them, so this is a subset of RD. And the volume, by definition, the volume is just, by definition, well, it's not very subtle. It's just the product of the lengths of the intervals. Okay, so not that there's any ambiguity, but I'm going to throw in a bunch of double dots here just to emphasize we're doing definitions here. So, and the same thing here. We're defining the volume. That didn't come out so well. Sorry about that. A little awkward here, but okay. There we go. Okay. So the definition of Lebesgue outer measure and the definition of the volume of a rectangle. Right. Okay. So maybe I should call these boxes, but whatever. They're higher dimensional analogs of boxes and rectangles. Okay. So the definition of measurability is basically the same. E is measurable if for any subset A of RD. The outer measure of A is the outer measure of A intersect E plus the outer measure of A take away E. So as before, the idea here is that, well, the idea is very simply that E is measurable if E cleanly cuts every subset of RD A, in the sense that you can write the outer measure of A as, well, the outer measure of the red plus the outer measure of the blue. Outer measure of the red is obviously, the red is A intersect E, and the blue is A takeaway E. Okay. And hence we say, that's why, like before, we say intuitively or rather E cleanly cuts every subset A of RD. It breaks up the outer measure into the red piece and the blue piece. Okay. Okay. So facts, the first, probably most important, or not the most important, but kind of the starting point. And this is actually not that easy to prove. It wasn't easy to prove for us, actually. To me, it's one of the trickier proofs we've ever done, that the Lebesgue outer measure of an interval equals the length of the interval. Well, it's tricky to prove this for higher dimensions, and is a little different than the proof for intervals, but the Lebesgue outer measure of a higher dimensional rectangle is its volume. And each higher dimensional rectangle is, in fact, measurable. That's actually pretty easy to prove. Okay. Besides that, virtually every proof of every result for Lebesgue measure on the real line very easily, almost trivially, extends to this higher dimensional setting we're at. In particular, if script M is the collection of all measurable subsets of RD, then this is a sigma algebra. That proof is identical to what's in the book and what we did for Lebesgue measure on the real line. And it contains all open sets. That's very easy. You prove that by proving that, well, every open set can be written as the countable union of rectangles. And that's actually pretty easy to prove. Actually, if you want, you can try that as a good exercise to do if you're bored. Got nothing better to do. I mean, I shouldn't say that. It's a good thing to do. It would be a 512 homework act. It might have been homework in 512. If I was teaching advanced calculus, I would have assigned that as a homework. But so we do the same thing we did before. We take the outer measure, restrict it to measurable subsets, and that is translation invariant, countably additive, continuity of measure is true. And additionally, you have that on actually all subsets of RD, Lebesgue outer measure is subadditive and monotone. And all these proofs are identical to the proofs for Lebesgue measure on the real line. Outer inner approximation is true. The proofs are very similar to the proofs on page 40. And particularly what's on page 40 is true. The definition of measurability of an extended valued function, where E is a measurable subset of RD, that's the same. All the measurability results are the same, and the proofs are identical. The proofs and statements of the simple approximation theorem, Egorow's theorem, and Lucen's theorem are basically the same, with one caveat, and that is the proof of Lucen's theorem is different. And the difference is Tietze's theorem is not, that's quite a bit different. The proof of Tietze's theorem is quite a bit different for higher dimensions. And that makes sense. What did we use to prove Tietze's theorem? We used the fact that every open subset of the real line can be written as the disjoint countable union of open intervals. That's not true in higher dimensions. You cannot write an open set as the disjoint countable union of open rectangles. You can do the next best thing, which is write an open set as the disjoint countable, or sorry, write every open set as the countable union of non-overlapping rectangles. And by non-overlapping rectangles, I mean you have two rectangles you say are non-overlapping if the interior are empty. So they could kind of you could have something like one rectangle like here and another rectangle like here, where they're both, let's say, closed rectangles and they share an edge, but the intersection of their interiors are going to be empty. Okay? That doesn't even really help you prove Tiz's theorem. And usually what you end up doing is just saying, the hell with it, we're just going to prove Tiz's theorem, and it's in a very abstract topological setting, which you do in I think 540A. I don't know who's teaching that in the fall, but if you're taking that, you will see a proof of Tiz's theorem. It's quite a bit more complicated than what we did. But once you have Tiz's theorem, then Lucen's theorem follows immediately in this higher dimensional setting. Okay, so Lebesgue integration, let's talk about that very briefly. So first, you integrate simple functions. Okay. So let's say E is a measurable subset of RD. Let's say this is simple. Definition is exactly the same. Simple function is just a function whose image is a finite subset of real numbers. Okay, so let's say the image is C1 through Cn with no repeats. So we're writing down the canonical decomposition of phi like before. So EI is the inverse image of the CI, or really the singleton CI, but whatever. So in that case, phi of x is going to be the sum here, and we define the Lebesgue integral just like before, just the sum Ci and the Lebesgue measure of EI. Okay, and remember this is basically how we this is basically what the Riemann integral of a step function was. Okay, so yeah, from this perspective, again, like we did before, this is not much different than Riemann integration of step functions. Just simple functions are more general than step functions. Okay, so what we did for Lebesgue integration was we next defined the Lebesgue integral of a bounded measurable function on a measurable not on a measurable subset, but on a subset of finite Lebesgue measure. So it is measurable, but the subset had finite Lebesgue measure. You don't really have to do that, and we did not have to do that. And I'll explain why we did that. So one alternative that you could have done, and we could have done, was just define the Lebesgue integral of a non-negative measurable function to be the supremum of all these Lebesgue integrals, and there should be a dx here. Not that it matters much, but little dumb things like that bother me. So anyway, so yeah, we could have defined the Lebesgue integral of a non-negative function as the supremum of all these integrals, where phi is simple, finite support, and phi is non-negative and less than or equal to f on E. Okay, so actually we defined the Lebesgue integral for a non-negative function a little bit differently, but homework was that these two are equal. Here we're going to define the Lebesgue integral of a non-negative function to be this supremum. You can really define it even if f is not measurable, but you really can't prove anything about this integral if f is not measurable, so there's really no point. But strictly speaking, the supremum makes perfect sense if f is not measurable, because measurable or not, you can always look at these integrals, and this integral, because phi is simple and has finite support, these integrals are all real numbers. So, and of course, this supremum could be infinite if the set is unbounded. Okay, so what we could do next is do exactly what we did before. If we have a arbitrary or a more general measurable extended real valued function that is integrable in the sense that take the absolute value and you integrate that, it's less than infinity. Then you define the integral of f of x, just like we did, the integral of f plus minus the integral of f minus. And because f is integrable, both of these are going to be real valued, so there's no ambiguity. Now, if you do all this, then all the basic properties that we proved, Fatou's lemma, monotone convergence theorem, and Lebesgue-Dame convergence theorem, these are all true. And particularly by the basic properties, I mean Lebesgue integration behaves very much like Lebesgue measure. Okay. Now, the proof of Fatou's lemma is a little bit different, but it's not much different. Otherwise, everything else is proved exactly the same. Okay, so a little comment on why we didn't do this. If I'm saying this path, this way of doing things is a little more efficient. Well, so like I said, what did we do? We first defined, like we do here, the Lebesgue integral of a simple function. Then what we did for Lebesgue integration on a real line is use that to define the Lebesgue integral of a bounded measurable function on a measurable set of finite measure. So why did we do that? And why do we choose to do that intermediary step and then use that to define the Lebesgue integral of a non-negative measurable function? Well, because remember we reformulated Riemann integration and Riemann integrability in terms of upper and lower Riemann integrals that themselves we were able to define that in terms of step functions. Well, when we define the Lebesgue integral and Lebesgue integrability of bounded measurable functions on sets of finite measure, we did that basically in the same way, just replace step functions with simple functions in the definition of Riemann integrability and the Riemann integral. So from that perspective, our path and the way the book does things, which is the way we did things, that way gives us a nice bridge of continuity from the Riemann integral to the Lebesgue integral. And as I mentioned a second ago and in previous videos, the definition of Lebesgue integration versus Riemann integration, particularly for bounded functions on a bounded set of or a set of finite measure. Sorry about that. They're basically the same, except you just replace step functions with simple functions. So that's why we did it, for pedagogical reasons. So for reasons of efficiency, like I said, we could have just done things this way. And most people actually do things this way. They just first do this right here. They just first define the Lebesgue integral of a simple function, and then they define the Lebesgue integral of a non-negative function, and then they say, okay, well, now we can trivially integrate basically everything else as long as we deal with integrable functions. So, yeah. Okay, so what I want to finally do in this video, and this is particularly relevant, well, it's relevant to probability theory, but it's also particularly relevant to the PhD preliminary exam. And that's, I want to discuss Fubini's theorem. And this is really the point of departure for the similarities between Lebesgue integration measure on the real line and in higher dimensions. And proving things I'm going to say gets very technical. If you really want to, you can look in the book on Fubini's theorem. They do things very abstractly, right. So to describe Fubini's theorem, we need to write an element of RD1 plus RD2, where D1 and D2 are positive integers, in the following way. So just write it as x1 through xd1 through xd1 plus d2. So we're going to use the notation x is x1 through xd1, so x is an RD1. Y is x, so it's a little hard to read, but this is d1, it's a little better. So it's x d1 plus 1 all the way to x d1 plus d2. So y is an r d2. Okay, so in this way we're very canonically and naturally identifying r d1 plus d2 as r d1 Cartesian product r d2 via, u equals x comma y. Okay. Okay, so something I'm not going to prove, because again, semester's over, and it would take a while to prove all these things. If you have a measurable subset of RD1 and a measurable subset of RD2, then their Cartesian product is measurable. So what is Fubini's theorem? Fubini's theorem says that if I have a measurable extended real valued function f that's integrable on E1 times E2. E1 and E2 are just like here. So they're just measurable subsets of RD1 and RD2 respectively. Okay. So if this is true, or f is measurable and non-negative, then first of all, for almost every x0 in E1, this function on E2, defined as just plug in x0 and plug in y, again, this is fixed here, so it's a really function of y. This is measurable on E2. Same thing holds for fixed y0. And the best you can do is almost every. You can't do every. So for almost every y0, this function here is measurable on E1. And basically, like in Calc 3, you can evaluate this integral. So this is, I should mention what this notation means. This notation here is the Lebesgue integral of f over the set E1 times E2 as a subset of R d1 plus d2. So in particular, the dx dy, I mean, really, I probably should really write this as f of u, and pardon my crappy drawings here, but I don't have my digital pen and pad here. Right. So if there's any confusion here, right. So this, I'm just saying the integral of f of u du over u in E1 times E2 can be written as either iterated integral, particularly doing E1 first, fixing y, okay? And I should say for, this integral makes sense for almost every y, this is measurable, and for almost every x, this is integrable. Okay, so particularly these two integrals make sense, and they're going to be equal to this. Okay, so two important notes. The first one I'm not going to use in the last bit of this video, but it's important to know. if you have f is measurable and g is measurable, where f is defined on E1, g is defined on E2, then the function f of x, or I don't know what you would want to call it, but the function, this function of x and y on E1 times E2 defined by little f of x times little g of y, this is measurable. Okay, more maybe importantly, for the end of this video, if you have an extended real valued function that's measurable and D is a subset of R that's also measurable, then this subset of E times D, instead of all xt, where x is in E, t is in D, and f of x is bigger than t, this is also measurable. So I should say this is measurable. Okay. And well, again, it's tough to write. I'm writing with my mouse, so. Okay, so what I want to finally do, and this is, well, this is important for everybody. You use this fact. You usually use this, like if in probability theory, you use this with respect to more arbitrary probability measures, probability spaces rather. And I should mention basically everything we're doing here, including Fubini's theorem, holds for Lebesgue, holds for abstract probability spaces. And in particular, you define integration with respect to abstract probability spaces, which is super important because you need that to define expectation and variance. You define integration of a simple function in the obvious way, and then define integration of a non-negative function in this way. Finite support is redundant there. And then you define integration with respect to an arbitrary function in this way. And by arbitrary function, we really mean random variables. Anyway, so what I want to prove, and this is often actually a prelim problem in various reincarnations. So if you have a non-negative measurable function on a measurable set, then the integral of this function is given by the following integral. Okay, and in probability theory, you have your probability measure here, your p, like in the previous video. So why is this important? Well, in pure and applied mathematics, probability theory, it says to prove facts about this integral here, which probability gives you facts about variances and expectations. It's enough to look at, well, the Lebesgue measure of this subset of E here. And of course, in probability theory, this critter here would be your cumulative distribution function. So in that sense, you can define, you can get that, you can define the expectation, or maybe not define, you have the expected value of a random variable as the integral of its CDF, which is useful. Again, if you have information about the CDF, then you know information about the expectation. Okay, so what's the proof? And the proof is a beautiful application of Fubini's theorem, and hence why I'm doing it. So first of all, where on earth does Fubini's theorem, or why on earth does this Fubini's theorem have any relevance to this? Well, that should be clear. In particular, I can write the Lebesgue measure of this as the integral of a characteristic function, because I'm just taking the measure of a set. Okay? And that set is x and e such that f of x is bigger than t for fixed t. Okay? So I'm going to plug this back into star, and star really is this whole thing here. So this is what I mean by star. Okay. So I plug this back into star. I get that this complicated looking integral, and I should make clear, as complicated as it looks, it's still really useful, really, really useful. I use it a lot in my research, actually. But anyway, so we can plug this back into star, and we get, well, one of these iterated integrals from Fubini's theorem. In particular, let's define this characteristic function here to be big F of xt, and notice that this is really a characteristic function of x and t with respect to x and t and e times 0 to infinity, satisfying the condition that f of x is bigger than t. Now this set here, this set right here I mentioned, is going to be measurable. That's exactly what is here. Okay, and same proof as in the proof for Lebesgue measure and integration on the real line. That means this characteristic function is measurable. It's actually the characteristic function is measurable if and only if the underlying set is measurable. Okay, so we have a non-negative 0, 1, this simple function. So we have a non-negative measurable function. We can use Fubini's theorem here. In particular, we don't even really care about this integral for this problem. We just want to know that these two are equal. Particularly instead of little f, it's big F, and instead of, well, E1, it's E, and instead of E2, it's 0 to infinity. I think I got the order right, but anyway. So, right, Fubini's theorem says that we can switch the order of integration. And here's where the magic occurs. And this proof is fairly simple, but it does honestly look like an incredible magic trick at first. So let's rewrite this big f of xt for fixed t. I'm sorry, not for fixed t. We don't want to do that for fixed t. We want to do it for fixed x because we're evaluating this integral for fixed x. Okay? So here x is fixed. So we're evaluating this integral for fixed x. Okay? Well, basically the same thing. Instead of saying xt is an e times 0 to infinity, that means x is an e and t is bigger or equal to 0. But still, f of x is bigger than t. Now think about it. For fixed x, we already have x as an e. So this is the same thing as saying t simply has to be bigger or equal to 0, and f of x has to be bigger than t. And in particular, when t is bigger or equal to 0, and when t is less than f of x, this is 1. When one of those is false, this is 0. Again, for fixed x. So in other words, for fixed x, f of xt is just this characteristic function. Well, this is a fancy way. I mean, it's not that fancy, but it's a fancier way of saying, a fancier way of writing the characteristic function of 0 to f of x. With respect to t, that's all this is saying. T is bigger or equal to 0 and less than f of x. That description of t is nothing more than t is in the interval 0 to f of x. So the integral from 0 to infinity of, well, f of xt is, because f of xt is this characteristic function, we know what the integral of this characteristic function is with respect to t. Okay? Don't let its bizarre look intimidate you. This is just an interval. This is an interval that's a subset of 0 to infinity. When we integrate the characteristic function of an integral, we get the measure of the integral. of the interval, not integral, sorry. This is just a measure of the interval. Again, don't let this weird looking thing intimidate you. For fixed x, f of x is something, f of x is, well, it's something, okay? It's something non-negative. The length of this interval from 0 to f of x, whatever f of x is, drum roll, f of x. That's it. It's f of x minus 0. Okay? So basically what this does is, I'm actually curious how the sound came out from that little drum roll, but anyway, f of x, sorry, this integral here is f of x, so we finally plug this back into here. And let me get rid of this. So this whole thing here is just f of x. Okay, I guess it doesn't like me going out of the boundaries. So I'll just try and sneak it in here. Right, so so this is f of x. So all star becomes, remember star is this complicated looking integral from 0 to infinity. This just becomes integral of e f of x dx, which is exactly what we want to prove. Right. Right, and that's it. So what I'll do finally for anyone who is taking the PhD preliminary exam now or later, I'll write some topics you're going to have to self-study. We did admittedly go at a snail's pace in this course, and I hope no one is angry about that, because I think it was necessary to do that, necessary to go really nice and slowly, and necessary for me to leave very little for homework, relatively speaking, and to fill in every detail. But anyway, hopefully this was interesting. And right, so 1 second. So if you are curious about what a nice, as I mentioned, a nice book or a nice kind of nice book to read, or nice chapter in a book to read on basic probability theory from the measure theoretic perspective, this is really good. You can find this actually PDF online. Just Google stochastic differential equations, Lawrence Evans. That's where I got it. Might even be on his webpage, actually. I think it is. Yeah, even just this chapter, chapter 2, it really talks about basic probability theory and from a perspective that really, picks up where we left off. I mean, it still does exactly what I did. It defines a probability measure and a probability space as, well, basically satisfying the same things I said. It's a little redundant here, but yeah, like I actually gave you this as a homework based on countable additivity, and I said this was a I said this was an axiom that the probability of the whole set is 1, and from this you can prove this. But anyway, so this describes, it actually describes a little bit more of the birthplace of probability with Bertrand's paradox and the Buffon needle problem. But it describes probability spaces, sigma algebras, events, et cetera, et cetera, characteristic functions, random variables. Well, here are characteristic functions. Integrating characteristic functions. Well, yeah, integrating non-negative functions, et cetera, et cetera, et cetera. So, yeah, so here exactly what I described is done on integrating random variables. But it also talks about joint PDFs, variances, Chebyshev's inequalities, the PDF, CDF, improves the law of large numbers, talks about, I think only one of the Burrell-Cantelli lemma, not the other one. The other one I think is a little more advanced in probability theory, but I mean, I thought it was kind of neat to prove. Talks about Fourier transforms of random variables, i.e. the characteristic function, which is often used to prove the central limit theorem. Yeah, I mean, I think they actually maybe prove the central limit theorem under certain conditions, or at least outline it. They prove Laplace-Demoivre theorem. They talk about Brownian motion. Of course, you need Laplace-Demoivre, do Brownian motion. Talk about conditional expectation, all this good stuff. So, yeah, plus if you're interested in applied math, stochastic differential equations is very, very useful in modeling just about anything in real life. But anyway, all right, that was, I'll end the rambling and hope everyone has a safe summer, safe, happy summer. I'll see some of you next fall, or if everything's on the line, then the spring. But all right, take care, so long, and do hand in your homeworks by the deadline, because I have to grade the homeworks and give you a grade basically one day later, so I really cannot accept them late. So anyway, bye-bye, take care.